Hi, I'm Saihari Kota, and today I wanted to talk about some manufacturing methods and tools that I find interesting. So first up, we have the high pressure die cast. This is one that I find interesting because at two of my internships, this was pretty commonly used for the production of some material parts. So that's why I wanted to talk about it. So high pressure die cast is a manufacturing process where molten metal is forced into a shape, into a die, and then the use of high pressures actually lets it get forced into that specific shape. Usually this can be used for very complex geometries and when you need high precision, and also allows for a pretty smooth surface finish. Because of that, you can find this in your usual aerospace, automotive, medical, and consumer electronics, but specifically something like some casings. That's where high pressure die cast is mainly used. Some of that exterior casings or like frame structural material for like a car or in a rocket capsule, or even like the phone casing for your phone for instance, could be from high pressure die cast. The main restrictions or limitations with this is that there's a lot of high initial costs. Obviously, you can't work with every material. It needs certain thicknesses, and because of that, some some geometry, such as like undercuts or like extremely thin walled geometry, may not be feasible. Furthermore, since it's using pressure and it's being entrapped in an enclosed area, there could be some trapped gases or air. And this is just
The die casting mold and tools are placed on the machine. The mold is then closed. Molten metal is injected into the die to fill the cavity. Extra material is forced into the cavity to compensate shrinkage during the cooling process. The plunger is held under pressure until the metal solidifies. The die can be opened once the metal is cooled. Next, the pins eject the parts from the mold. The sprues are still attached to the parts and have to be removed. After that, the individual die-casted parts are ready for the next stages.
Another thing that I forgot to mention was actually this is pretty also common in making engine blocks and stuff like that for the automotive industry. As you can see, that was kind of similar to some parts you could see in an engine block. Next, another process that I find extremely interesting and fascinating is silicon packaging. This is actually kind of what I did automation controls for as an internship for a silicon packaging production line over the summer, and where I plan on returning to full time as well. So this is definitely something I find extremely interesting. So silicon packaging is a manufacturing process that involves, obviously the process of enclosing a semiconductor device in a protective shell or just packaging that semiconductor device to be usable. And obviously this is extremely important for everything, all sorts of electronics. But specifically for that, it really helps with protection from any external environment, such as like dust, moisture, any mechanical damage, heat to some degree, helps with heat dissipation from the actual chips themselves, and makes reliable electrical connections. And so there's several methods to silicon packaging. There's system and package, flip chip, and chip on board, all with their own specific advantages and disadvantages. And as a quick overview through all three, system and package has multiple chips or components integrated within a single package. And this really helps for compact systems when you're trying to reduce the size, the cost. And the great thing about this is obviously, you can put this in like wearable technology or like anything that needs to be extremely small, because now you have everything in one specific package. However, due to all these components being enclosed with one another in such a small area, their thermal management is pretty difficult. When you have a chip on board, this would just be a simple silicon die that goes on top of a PCB. Pretty low cost. You can make them in very high volume. This is what you very commonly would see in LEDs, stuff like hearing aids, and you can see this all over the place. It's pretty simple. It is connected through wire bonds, as you can see here, these little wires that connect the silicon die to the PCB. Now, flip chip is very similar to a chip on board, but uses a ball grid array of solder balls, very small solder balls, and it's an array of these solder balls, and this is what connects that die. And this is a lot more efficient as you're using the solder balls for the connection instead of these wires, so it's a lot better of a connection. However, it's much more expensive as now you have to get all these solder balls and stuff. And as you can see, this is just one silicon packaging machine, just taking silicon dies from a wafer. And the really cool thing about silicon packaging production is it's extremely high speed and high accuracy, because it's this very small size that we're manufacturing with, which is really cool. So next, I wanted to talk about wire electrical discharge machining. I just find this one really cool because, as you talk about, it can achieve extremely high precision cutting. So basically, wire EDM uses an electrically charged thin wire, usually something conductive like copper or something, to cut intricate shapes and tight tolerances into hard materials. And this could be used in like jet engines, surgical equipment, any high precision molds, basically anything that really needs a ton of high precision and tight tolerancing, which is what wire EDM is great on. It's also great on hardened materials. As you know, you don't need to do the hardening afterwards. You can have a hardened material already, and wire EDM can actually cut through that because it actually it uses the electrically charged wire to actually cut instead of it just being a normal blade or something. Restrictions is expensive, obviously. Otherwise, this would be used a lot of places, but it's mainly only used when that amount of high precision is absolutely needed. Otherwise, you can use other manufacturing processes. And this is just a video of how tight of tolerancing you can get. Like that initial block looked like it was not cut at all, basically, because that's how tight the tolerancing can be, and it's really cool. And then fourth up, we have thread rolling. I just think thread rolling is important to talk about and learn about because it's extremely used everywhere. I mean, fasteners are all over the place. And thread rolling actually allows us to get a stronger and more precise way to make these threads on metal instead of your general thread cutting. And this is something that I specifically like because as part of my robotics team, we have to make a lot of threads. And sometimes I have had to actually get those threads machined, and I've opted for thread cutting, which sometimes does not meet the specifications we need, and sometimes we need to go for thread rolling for those stronger threads so that it won't break as easily. And as such, these are used a lot in your usual aerospace, obviously extremely strong fasteners, but also like automotive and cars near like the transmission and engines because these are susceptible to high vibrations. So these threads need to be extremely strong. And by rolling these threads, instead of cutting, you're kind of forming the thread, you're moving that material, deforming the material. And that allows for higher reliability, a lot of strength, as I mentioned, great surface finish, and this can be used in pretty high production speeds as well. Only restrictions is obviously since you're kind of like deforming that material, you can't really use brittle materials. It needs to be much more ductile materials for thread rolling. And here's a video of thread rolling happening. As you can see, you actually want a cylindrical blank for thread rolling that has an outside diameter that's already in the desired thread diameter range, obviously, because then you're going to cut into it or roll into it. And then you can see the thread rolling itself happening. And this gives you a pretty good idea of how it actually will roll it. And then furthermore, compared to cutting itself, as I mentioned, since it's not actually cutting the material itself is less brittle and much more stronger once it's rolled, opposed to cutting, as you can see here as in the side-by-side. Lastly, I wanted to talk about incremental sheet forming. I think this is extremely cool because you can take sheet metal and just make it into pretty weird shapes, but in a pretty like straightforward way. Some of these other processes like wire EDM are much more complex, whereas sheet forming for the most part is kind of simple in the sense that you're just forming the sheet metal by just small incremental deformation of the sheet using this rounded tool. And I think that's pretty cool. It's just you're slowly deforming it. And this can be used in like, again, automotive with car bodies and stuff, prosthetics for like that, like a casing for like a knee or something or elbow. And the great thing about incremental sheet forming is since it's using sheet metal, it's pretty flexible. You can make a variety of shapes or work with a variety of sizes with a single machine, and that makes it somewhat lower cost as well. The restrictions are that it's slower. It needs specific material thicknesses. Obviously, if it's too thick, it's not going to be able to properly deform it. And then also, since this isn't anything fancy, it's going to be a much rougher surface finish. So if surface finish is something you're concerned about, if it's like a customer-facing body or something, then maybe you don't want to use incremental sheet forming. But if it's something internal and purely structural, then this could definitely be used. And this is just you see the rotating blank, and then the tool comes in, and Just can incrementally form that by going in. It's pretty cool. Here are some of the resources I used. And as always, thank you for watching. And as a heads up, this content was created by a student who's still learning about design and manufacturing. And as such, don't take anything for fact. It's produced to the best of my knowledge from my experiences and what I looked up and learned about.